So we're going to need to read this carefully. A lot of definitions, a lot of terms. You need to understand these clearly to do the problem. So, going straight to it, we're going to create sequences of letters, and they only contain A and B. And they're called strings. Those of you who do computer programming may be familiar with that type of idea. A string has a length, and if it has a length n, we call it an n string. So they've given us an example here of a string like this. Bar, bar. And it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. So it's called a 12 string. All right, now they talk about the idea of a substring, and that gives you a clue what that is. A substring is going to be a piece of a string. So here's a substring, bar, and here's a bar. So it can appear more than once. So here's a bar and here's a bar again. That's okay. So for example, this particular one contains R, AA, 3 times. And it doesn't contain a substring bar. Okay, right. So we need to understand the idea of an N string, a substring, and the final piece of our puzzle is the idea of a palindrome. So a palindrome, I think you know those. They're like this one, Adam, Madam, I'm Adam. And this is one of those fun phrases you can read in that way, or you can read it backwards. Madam, I'm Adam. So it's the same backwards and forwards. Okay, here comes the key idea. Every 3 strings, starting with A, here they are, there's a little table. You're going to need to get used to this idea of setting problems on a table, has exactly 3 different palindromic substrings. So if we look at A, it's got A. Oh, that's interesting. A palindrome can be just one letter. AA. Let's look at this one. ABB. It has just A, just B, and BB. I notice when they list these, they first list palindromes with 1 letter and then palindromes with 2 letters. That's giving us, and then palindromes with 3 letters. That's giving us a clue what might be a good way to list these palindromes. So question A asks us, is about 3 strings. Now in the table we had 3 strings that start with A. It's now asking us about the 3 strings that start with B. And it says, we said all the ones that start with A have exactly 3. Can you explain why it follows that if they start with B, there are also 3? Now, be aware this word explain isn't the same as show. So you could show it. If you don't see the answer to this straight away, you could actually show it. You could start by listing the strings that start with B. Okay, I'll let you think how many there are, and then you could list their palindromes. But once you look at it, you need to explain why looking at the first table automatically tells you that it works for the second. So part B now moves us to 4 strings, but notice it's only asking about 4 strings starting with A. And what we want to prove is that every 4 string that starts with A, so let's look at what a 4 string, its general shape would be. 2, 3 would be like that. Something like that. And we want to show that all of them have exactly 4 palindromic substrings. And notice this time the word is show. So we don't have to explain why, we just have to show it. So we could just list it. Now I'm going to ask you to think, how many of these strings should there be? If you're not familiar with some combinatorics, I'm going to show you the technique. So the first one must be A. We ask ourselves, how many choices do we have here? We can put an A or a B, so there are 2 choices. Here, we can put an A or a B, so there are 2 choices. Here we can put an A or B, so there are two choices. There's only one choice here, it must be an A. So the total number of strings starting with an A is 8. So you're going to have to work through the 8 strings and find all their 4 palindromic substrings. Part C is asking us about every 5 string, and this time it's every 5 string, not just starting with A and B, all of them. Now it's a show question, so we could just list them all, and we're going to ask how many are there. 5. So I'm going to draw a little box with 5. So in the 5 positions, 1, 2, 3, 4, 5. So I could put an A or a B in there, an A or a B in there, on there, and there, and there. So the answer is actually 2 by 2 by 2 by 2 by 2, or 2 to the 5th, which is 32. Do I really want to list 32 strings? No. Mathematicians are very lazy. They're not going to do any more work than they have to. So we're going to think carefully. In the previous 2 questions, we only looked at strings that start with A or start with B. And we reasoned why once we'd found the answer for A, we had found the answer for B. Do you remember that question? That was part A. Now part B asked us about 4 strings. This is asking us about 5 strings. Now I'm really hoping to avoid doing 32 combos. Can I use the information from the first 2 parts to minimize the amount of work? Can I use the result for A and B and for 4 strings to help me with 5 strings? You'll discover that if you start creating the tables. So we've now proved that for every 3 string, it has 3 palindromes. Every 4 string has 4, and every 5 string has 5. And we begin to think there might be a pattern. And it turns out it is true that every 6 string has 6, every 7 has 7. However, the pattern's going to break. So we're given the information that for an 8 string, there are some that don't have 8 palindromic substrings. Now they're giving us a clue. They want us to find an 8 string. So there might be more than one. I'll leave you to work that out. It starts with that. And we've got to find one that's only got 7. All right, so just to give you a starting clue, let's consider how many there are. A, B, B, A. 1, 2, 3, 1, 2, 3, 4, 5. Okay, so we're after an A string. So there could be 2 choices here, 2 choices here, 8. That's good news. We're only going to have to check 8. Now, it could be quite painful to list the 8 palindromic or less for each. So we're going to see, can we reuse some of the previous data? And again, I'll let you explore that. I think you'll be quite surprised, pleasantly surprised by what you find. So just to finish off talking about this problem, I'm really interested in why. Why does it break? Does it break with the 8 string? I'm kind of curious. Normally when something works for 1, 2, 3, 4, 5, 6, 7, you'd expect it to break for 8. But it is a warning never to assume a pattern follows until you can prove it. So I'm kind of curious, why does this pattern break when we get to the 8 string? I actually don't know enough about this type of problem, and I'm kind of tempted to explore it a little bit more. There's a reference in the teacher handbook to an algorithm called Manicher's algorithm as a way of finding palindromic strings. I'll write that name in big in case you are a computer programmer and are interested in this Manicher's algorithm. And there is a reference in the teacher guide to this, that strings have lots of applications. I didn't know about this one. I did know it has an application to DNA sequences. That kind of makes sense when you think that DNA is typically, what was it, ACGT, different sequences that make the genomes. And like so many parts of maths, it's important for cryptography. All right, I'm going to leave you to have fun with this problem.